Hello everyone, welcome to Statistical Foundation for Big Data Analysis. So in last class we saw Erdős-Rényi random graph and we discussed how it behaves as n goes to infinity, because the generating probability, we recall that like Erdős-Rényi random graphs where like you have bunch of vertices, n vertices, and for each pair of vertices potentially the edge can be there or edge cannot be there. Edge joining them, you kind of independently for each vertex you toss a coin with head probability p for all of them, one at a time. If if the toss gives you head, you take that edge. If it gives you tail, you don't take that edge. Whatever the totality is, that gives you a random graph. Now we generally this head prob we talked that this head probability is p is a function of n. As n goes to infinity, what happens is something interesting, and we gave you some example. We also did some small calculations with random graphs like expected number of edges, expected number of triangles, etc. So these calculations, calculating these expected values as well as these general theories we were discussing without proof, the behavior of the whether the graph is connected as n goes to infinity with high probability or not, etc., that we were discussing, this connectivity threshold, etc. In few lectures from now on, we will do some such results very rigorously, just to give you a glimpse of how this so called law of large number for random graphs, that is the behavior of random graph as number of vertex goes to infinity, pans out. But before we do that, just a quick review of some of the basic topics from law of large number in classical probability. Just the first result, which is very useful, just a general inequality. This has nothing to do with law of large number. So if x is a non-negative random variable, discrete or continuous, and suppose k is just any real number, and this is actually called Markov inequality, by the way, this inequality. So the probability of x being greater than or equal to k is actually bounded about by expected value of x divided by k, or basically k times probability x greater than or equal to k is less than or equal to expected value of x. This basically follows directly from the definition of expected value, which we will see immediately in the next slide. So rewriting this whole thing, you can actually write that if you replace k by k times expected value of x, expected value x is a constant. So you will get probability x being greater than k times expected value of x is less than or equal to 1 over k. So this is basically your classical Markov inequality. So we will give you a very quick proof because it is fairly elementary. We will give you a PDF version of this. For the discrete, you can modify this integral into sum, and more or less will follow identically, because for the discrete case just integral will be replaced by sum and all other arguments go through intact. So expected value is you basically integrate or sum x times its PDF or PMF from 0 to infinity. Recall that we have assumed that x is a non-negative random variable. Now if you are doing for this for k, so split the integral or sum from 0 to k and k to infinity. Now the point is this integral, this function is greater than or equal to 0, and in from k to infinity, this region, the value of x, so this is a non-negative integral, and in this region the value of x is at least k. So this is k to infinity. So this integral is actually bigger than or equal to k times fx dx, k to infinity, which is equal to k times k to infinity fx dx. But what is k times, but what is this? This is nothing but probability x being greater than or equal to k. So expected value of this is just, and this is the non-negative term, this is non-negative. So expected value x is some non-negative terms plus k times probability x greater than or equal to k. So this gives you what you want, expected value of x greater than or equal to k times probability x greater than or equal to k. This is basically your Markov inequality. So, I mean, you can rewrite it in as many ways as you want. Probability x greater than equal to k is less than equal to expected value of x divided by k, or various other ways. But this is essentially just splitting the expected value, the sum or the integral that is involved in calculating expected value into 0 to k and k to infinity, and observe that the basic behaviors of non-negative functions. So, this is quite useful in proving one of the most rudimentary law of large number. I mean, in this talk we will actually delve little deeper into law of large number for general random variables, and then kind of from there come to the law of large number for random graphs, because this will actually allow you to appreciate the behavior of random graphs when you are making n goes to infinity a little better, at least from a mathematical point of view. So, this is the proof that we were discussing. You just split it into two parts. So, expected value of x for k from infinity, expected value of x times f x dx is just greater than equal to, you just replace x by k, because all over this interval x greater than equal to k. So, replacing by k, you can only go down, k is a constant, goes out, and whatever is left is the probability. So, that gives you the expected value greater than this probability. Now, Markov inequality immediately leads to something called Chebyshev's inequality, where if you take x to be any arbitrary random variable with mean to be mean mu and the variance sigma square. Let us say you have finite mean and finite variance for every epsilon greater than 0, probability of absolute value x greater than equal to epsilon is less than equal to sigma square divided by epsilon square. Now, this is immediate from Markov inequality. This is nothing but probability. This is identical. This is just same. If absolute value x minus mu greater than equal to sigma square, if epsilon square is nothing but x minus mu square greater than epsilon, but by Markov inequality it is less than equal to expected value of x minus mu whole square divided by epsilon square, and this is variance, which is sigma square. Immediately follows from Markov inequality. So, this is what I just wrote, is written in more details here. So, you just replace in the Markov inequality x by x minus y whole square y, and you are asking for any a. You know that by Markov inequality probability y greater than equal to a is less than equal to expected value y divided by a. So, in case of y you put x minus mu whole square greater than equal, and in place of a you put sigma square, you just immediately get this Chebyshev's inequality. Now, using Chebyshev's inequality, we prove a very fundamental result called weak law of large number. So, if x1, x2, xn dot 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 xi is a sequence of independent random variables with common expected value and finite variances, such that summation of the variances of n of them divided by n square goes to 0 as n goes to infinity. For example, if suppose all the variances are same, this will hold particularly. Example, variance of xi sigma square for all I. Suppose this holds, then of course you will get this condition, then 1 over n square summation variance xi I running from 1 to n will be n sigma square over n square, which is sigma square over n, just like that happens in case of sample mean. This will go to 0 as n goes to infinity. So, this is basically a slight generalization of the constant variance setup. So, now because we are taking infinite sequence for sample mean, we insist that using this x instead of x bar, x n bar to denote the sample mean of first n of them. Then with probability p, x n bar goes to mu, this expected value mu, this common expected value, which means the following, that as n goes to infinity, the difference between x n bar and mu essentially vanishes. That is, for every epsilon greater than 0, you can choose epsilon as big or as small as you want, you choose epsilon very, very, very small, arbitrarily small, still the probability that xn will remain inside the epsilon neighborhood of mu is almost 1 as n goes to infinity. So, pick epsilon very small as n goes to infinity, probability xn bar belongs to this neighborhood mu minus epsilon plus epsilon goes to 1. So, the sample mean for large and large sample essentially becomes, and you can choose epsilon as small as you want. So, essentially what is happening, xn bar is becoming equal to epsilon. So, in loose term, as n goes to infinity, sample mean becomes more or less same as population mean. Only condition, of course, you have to have that, like, it's being finite and the variances satisfy this condition. If you have IID sample, of course, this will IID sample with finite mean and variance, definitely these conditions are satisfied. Our setup that we wanted. I mean, here we are taking a slightly general version, because just to give you an idea that, like, these laws of large number may even hold for slightly more general scenario also than just taking constant variance, which has some application in the context of random graph theory. But in general, you can even think all the variances to be identical to some constant sigma square, and this condition will obviously be satisfied. So, with this and the Chebyshev and Markov inequality in our bag, we embark on proving this, and it will be good if you kind of try to understand this proof a bit. This gives you kind of nice insight of asymptotic behavior. Now, mean and variance, let us compute the mean and variance of the sample mean. The linearity of the expectation gives, of course, when you write down xn bar, the formula, write it out completely instead of using summation sign, x1 plus x2 dot 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 xn divided by n. So, n comes out. So, each basically expected sum of the expected values, each have expected value mu. So, it is just mu, n mu divided by mu. So, it is mu. What about variance? Variance of xn bar is 1 over n summation of the variance xi. These are independent. So, it is 1 over n square variance of, so these are independent. So, 1 over n square variance of xi, and each of the variance, each of the xi is a variance sigma I square. So, variance is 1 over n square summation sigma I square. Now, as n goes to infinity, what we do, we apply Chebyshev's inequality on this. What is the statement? The statement is, for every epsilon greater than 0, this probability goes to 0 as n goes to infinity. Now, replace or bound this probability by expectation. So, the key of Chebyshev's and Markov inequality was the probability of x being bigger than something can be bounded above by expected value divided by some constant. What happens if you do that? So, particularly for the Chebyshev's inequality, expected value of this being bigger than epsilon, a probability of this being bigger than epsilon was bounded above by sigma square over epsilon square. Now, what is the variance of xn bar? Variance of xn bar is just this term we observed here. Now, as n goes to infinity, we know that this term goes to 0. Hence, for every epsilon, the right hand side goes to 0, exactly what is asked for in this theorem. This gives us a complete proof of weak law of large number. Now, we apply weak law of large number in certain way, or we sort of, in this course, in next class we will see, we will prove a weak law of large number for random graphs. Now, for us, in case of random graph, the theorem that we will prove that if you take n vertices labeled by 1 to n, and suppose you are basically for tossing a coin independently for each potential pair of vertices, and if you get head you take the join them, if you get tail you do not join them, and subsequently you take the resulting random graph. If you take the number of triangles in that random graph, we discussed expected number of triangles in a random graph and we computed that value. If you take the delta n for a fixed n, if you take delta n to be the number of triangles, is of course a random object, random variable, you divide that by expected number of triangles, that is a constant, expected value is a constant, of course depends on n and p, but it is not random in a sense, it cannot potentially, different graphs can have different triangles. So, for a particular graph delta n will be something, for two different graphs it can potentially be different. So, it is a random thing. Expected value is a constant. If you take their ratio, as n goes to infinity, this goes to 1. So, in particular, on an average, expected number of triangle and number of triangle becomes same for a random graph as n goes to infinity. Compare this with this. Here we are saying essentially as n goes to infinity, the average of this sample, the sample mean becomes identical to the population mean. Here we are saying if you take for large n, you take a random graph, the number of triangles in that random graph, or as n goes to infinity, the number of triangles in the graph, any random graph for large n becomes basically same. Just like x n bar basically becomes a constant random variable, constant taking value mu with probability 1 approximately. Here you take a very large random graph, the number of triangle will be a constant almost with probability 1, because this ratio will be almost identical to 1. So, as n goes to infinity, another way of saying this, if you count the number of triangles in the graph, it kind of stabilizes to a fixed value, and that fixed value will be expected number of triangle for a size n random graph for each dimension n. Now, I am using the word dimension because there is a slight difference, a very subtle difference between what we were doing in case of law for large number in general and this one. In case of law of large number, for each n you are drawing a random graph x n which has this expected value mu which is constant and variance sigma I square. Here as n evolving to infinity, n going to infinity, your x n is a random graph, Erdős-Rényi random graph on n vertices. Potentially we do not know what is the expected value. Well, what do you even mean by expected value of a graph? You can of course talk about expected value of various features of that. For example, we are talking about number of triangles in that graph. Now, there in the weak law of large number, mu was constant for each x n, is each x I, and you are taking average of n of them. So, of course, the expected value was mu. Here for each n, the expected value of this delta n, that is number of triangle, will be different. In fact, we saw what it will be in last class, but still what we are saying for you, so you really cannot talk about same way, because you are changing the dimension and the expected value actually depends on n. You really cannot expect the expected value to be some dimension free constant, but if you take the expected proportion, like this is the expected number of triangle in all random graphs of a fixed dimension, and let us say you take for a particular random graph, you divide that by this total number of graphs, you sort of normalize the the number of triangle by expected number of triangle, that number becomes almost identical to 1 as n goes to infinity. That is, if you draw a random graph for a very large number of vertices, for that particular number of vertex there is a number, the for that number of vertices there is a number which is calculated from that formula we proved in last class. With almost 100% certainty, the number of triangle in that graph you selected will be same as that number. So, in particular, what was the expected number of triangle? So, expected number of triangle delta n was n choose 3 p cube. So, as delta n as n goes to infinity, delta n becomes identical to n choose 3 p cube. That is, with all random graphs on n vertex has approximately n choose 3 times p cube many triangles for n infinity. I mean, you can interpret in as many intuitive way as you want, but the formal way of saying is precisely this statement. So, if you take the difference between actual number of triangle in a particular random graph and the expected number of triangle, in case of that the previous law of large number, you are taking absolute difference between expected value and the actual value. Here you cannot do that, but if you take the ratio, that expected number of triangles in that particular dimension, that particular n, and that expected number comes in the denominator, and in the numerator you take the actual observed number of triangles. This ratio becomes closer and closer to 1 as n goes to infinity. So, you can choose as small neighbor epsilon as you want. So, for basically for large n, delta n divided by n choose 3 p cube belongs to 1 minus epsilon p, 1 plus epsilon for all epsilon greater than 0. However small epsilon you choose, this will happen. In some sense, this so called what we are writing a weak law of large number for random graphs is also a law of large dimension. I mean, n is increasing in case of random graph means also number of features increasing. So, here number is not just you are taking many random graphs, you are kind of higher the dimension goes, you are getting a newer and newer random variable. It is also you are adding new dimensions. So, these numbers are not just arbitrary number, you are actually increasing the dimensions. So, this is how a potential law of large number for random graph may look like. In next class, we will try to give you a rigorous proof of that, and then we will move on to other topics on random graph on subsequent lectures. Thank you very much. I stop here.